Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, so now we continue our new chapter, chapter 5, hydraulic structures. Okay, so in this hydraulic structure, students should be able to recognize the use of various types of hydraulic structures. Okay, estimate the rate of flow through or over various hydraulic structures, and design USBR stealing basin type 3. Okay, now we look at what is the hydraulic structure. Okay, hydraulic structures are artificial or natural structures that can be used to divert, restrict, stop, or manage the flow of fluid. Okay, the structures can be made from a range of materials such as large rocks, concrete, wooden timbers, or even tree trunks. Okay, one of hydraulic engineering works is to design and analyze hydraulic structures. Hydraulic structures is constructed to control flow, okay, maintain water level, control erosion, and others. Okay, example of hydraulic structures are sluice gate. So we have learned the sluice gate based on the rapidly varied flow, okay, gradually varied flow, spillway, and so on. So now we just more advanced. What is the hydraulic structure? Okay, sluice gate, the spillway, weir, energy dissipator structures, and constrictor. Okay, this is the sluice gate. Okay, based on the sluice gate here. Okay, and this is also the sluice gate based on the sluice gate, then the spillway here, this in the dam, okay, and the spillway, okay, and the weirs here based on the type of weirs, okay, based on the weirs, based on the sharp crested rectangular weirs, and so on, broad waisted weirs. So we have learned in chapter 3 and chapter 4. Okay, energy dissipator here, so this is the energy dissipator, okay, based on these types here. Okay, so sluice gate. Okay, sluice gates are used to control and measure rate of flow in open channels in hydropower plants and irrigation channels. So this is the sluice gate. Okay, the sluice gate here. Okay, and we know that the Y knot, okay, before the sluice gate, and you have also known the hydraulic jump, and get the Y2 here, Y1, okay, before the jump, and after the jump is Y2. Okay, so we know that E naught is energy specific, initial specific energy. Y naught is the depth of flow upstream. Okay, in the Y naught is the upstream. The Y2 is the depth of flow for the downstream. Okay, and A is height of the gate opening, and the Y1 is depth of flow downstream. Okay, the flow under the vertical sluice gate is considered as rectangular orifice as long as the height of the gate opening A is smaller relative to specific energy EO, and the flow further downstream Y2 does not affect the flow under the sluice gate Y1. Okay, the minimum depth area, maximum flow velocity immediate downstream of the sluice gate is known as vena contracta. Okay, the depth of flow at vena contracta Y1, okay, is equal to the depth correction factor here based on this value, range value. Okay, flow under sluice gate, okay, rate of flow under the sluice gate can be derived from the Bernoulli theorems. Okay, so based on the Bernoulli theorem that you have also used here. Okay, since the free surface is under atmospheric pressure, V0 is equal to P1 is 0. Okay, upstream velocity V0 is very small compared to downstream velocity, thus V0 is equal to 0. So there, Y0 minus by Y1 is equal to V1 squared over 2G. Okay, so velocity of flow under sluice gate, so we here, and also the rate of flow under the sluice gate is like this formula here. Okay, so based on the CD, coefficient of discharge is based on this range. Okay, so all this formula is given. Okay, no need to worry. Okay, if downstream control Y occurs Y1 submerged completely, and the rate of flow is based on Y0 minus by Y1, sorry, Y2. Okay, rate of flow under sluice gate is Q based on this formula. If y0 minus by y1 is more than y2, okay, you use this formula. Okay, when y0 is equal to y0 minus y1 is less and equal to y2. Okay, so based on this formula. Okay, so example here, activity 5.1. A sluice gate is built in a rectangular channel with bottom width B of 2.5 meter. Okay, the flow and gauge characteristics are y0 is equal to 2 meter. Okay, the symbol of this one, okay, 0.625 CD and so on. Okay, calculate the discharge under the sluice gate if y2 1.8 meter. Okay, so the given parameter is this here. So now you just use the y1 here. Okay, the symbol is actually is the coefficient. Okay, so y1 is the coefficient times by the a here, coefficient of the vena contractor. So 0.625 times by 0.5, so you get this value. Okay, condition of control, so you get this y0 minus by y1, so equal to 1.6875 meter. Okay, since y0 minus by y1 less than y2, so use this formula. Okay, you use this formula and put all the value that you get, and then you get the Q. Okay, actually this is the direct formula that you use. Okay, so the vena contractor coefficient is given, so you just use that formula and using the parameter given, so you can get the Q. Okay, so now we look at the spillway. Okay, spillway is built in a reservoir to allow the flow of water to safely move downstream when the reservoir is full. Okay, so a spillway is shaped as a rectangular concrete. So in this part, so all the spillway, okay, all the sluice gate. So this is more on theory, okay, for this hydraulic structure. Okay, a spillway is shaped as a rectangular concrete channel that connects the upstream and downstream regions of a weir. Okay, the best design of spillway is following the lower net of free fall or flow, especially is OG spillway. So based on this spillway here, and the base shape of the spillway surface is parabolic based on the parabolic here with inverted curve at downstream. This is inverted curve. Okay, inverted curve. Okay, and this is based on the parabolic. Okay, so this is the shape of spillway surface. Okay, is parabolic with inverted curve at downstream. Okay, so this is the Sembrong Dam spillway. So in Sembrong Dam spillway is based on this one. So this is the spillway here. Okay, and also the, okay, you get the, okay, so now we look at the OG spillway. Okay, OG spillway is also known as the overflow spillway and is widely used on gravity arch and buttress dam. It is the most extensively used spillway to safely pass the flood flow out of a reservoir. Okay, OG is the shape based on the underside curve of the nap over a sharp crested weir. Okay, based on this, okay, based on that figure. Okay, so in high overflow spillway H1 more than HT, the discharge corresponds to the maximum design capacity of the spillway, and the crest of OG spillway rises up from point A okay, to maximum rise of 0.115 H1, okay, to maximum rise of, then falls in parabolic here. Okay, so discharge coefficient CD for OG spillway is about 20% higher than CD for weir. Okay, so this is more on theory. Okay, and this is the weir. Okay, what is weir? Okay, maybe in your final ask you to define what is weir, what is the spillway, okay, what is the sluice gates. Okay, the weir, a weir is an overflow structure built across an open channel to measure the rate of flow. Okay, the weir offers a simple and reliable method of measuring the stream flow. Okay, so this is the nap here, and this is the sharp crested weir. Okay, they have the H1 and the P is the height of weir and Q is the rate of flow. Okay, weirs can be classified into various types based on the width of the crest and the opening of the weirs. So the based on width of crest, so there's the broad crested weir and sharp crested weir. Okay, based on opening of weir, so this is a rectangular notch, trapezoidal notch, and the triangular notch. Okay, so this is based on the width of crest and the opening of weir. Okay. Weir has a broad crest when the thickness of the crest is more than 60% of nap thickness. So nap actually is the nap here. Okay, based on the nap. Okay, so weirs can also be categorized into submerged and non-submerged weirs. Okay, so the rectangular weirs. So rectangular weirs are divided into suppressed weir and contracted weirs. Okay, a weir is suppressed when the weir opening spans the full width of the channel. So the discharge Q over a sharp crested, fully ventilated and free-flowing suppressed weir is given as this formula. Okay, so Q is equal to 2 over 3 CD times by 2G, LH, and so on. So all these formula is given. Okay, no need to worry. Okay, the formula is given, but it's not mentioned that this formula is for rectangular weir. This formula for what? Okay, so you must familiar this formula is for rectangular weir or not. Okay. Okay, and the discharge coefficient is also given. Okay, so this is based on the Rehberg formula. Okay, so based on the H1 over P less than 5, H1 over P, the range here, okay, and the H1 over P is more than 20. So this is based on the range of CD to get the CD. Okay, so example here, activity 5.2, a suppressed rectangular weir 0.575 meter high and 1.5 meter long. Okay, 0.75 meter of the suppressed rectangular weir and 1.5 long is used to discharge water from a tank under a head of 0.5 meter. Estimate the discharge of the weir. Okay, so the suppressed rectangular weir, so we know that the P is 0.75, L is 1.5 and H1 is 0.5. Okay, so you find using this formula H1 over P, so you get the value here 0.6667 here. So H1 over P is less and is equal to 5 here. Okay, so using this formula, so you get using this formula. Okay, and then you get the CD is 0.661. Okay, so you get the CD is 0.661. Okay, and then you just put the CD in this formula and until you get the Q. Okay, so actually for this chapter, so you just direct use the formula. Okay, so now we're using the contracted weir has weir length that is smaller than the width of the channel due to the presence of the end contraction. So the effective length of weir L is smaller than the actual length of weir L. Okay, based on the L here and LE here and the B here. Okay, and P and also H1. Okay, so contracted weir can be contracted at both ends. Number of contraction N is 2 or only one end, N is 1. So for suppressed weir is N is equal to 0. Okay, 2 end contraction, so the N is 2. Okay, because you have the 2 end contraction. Based on the 2 end contraction weir, so you get the N is equal to, okay, 1 end contraction only. Okay, so the N is equal to 1. Okay, no contraction here. Okay, 0 and contraction, so N is equal to 0. Okay, so this is, okay, maybe in your questions, final exam or so on, so they give you the figure. Okay, you just explain what is that figure. Okay, so maybe they give you this figure and you must know that the end of this figure or so on. Okay, so now we look using the rectangular contracted weir, use this formula. Okay, based on the L, okay, and the LE, okay, LE based on this one, okay. So this formula is also given, okay, and number of N contraction, H1 is H of flow over the weir, and CD is coefficient of discharge, okay. Coefficient of discharge, you use the Basin formula. So this formula is also given, okay. If you want to find the Q based on the rectangular contracted weir, okay. So now look at the example here. Estimate the discharge if the weir is discharging water from a tank under a head of 0.5 meter. Okay, so just direct use the Basin formula, and then you get the CD. After you get the CD, you find the LE, and then just do this formula and put all the value until you get the Q is 0.9796 meter cubic per second. Okay, so this is the direct formula that you must use, okay, in the question. Okay, so now look at the triangular weir. Okay, the triangular weir, you use also this formula. Okay, so no need to worry. If the questions you look at, they give you that formula, triangular or rectangular weir, so they must just give you the one only. So that one weir that you use, so that formula that you will use, okay. That formula is given, so that you must use that formula. Okay, so you get the CD here, okay, and put all the value to get the value of Q. Okay, the calculate the discharge or flow through a triangular notch. Okay, this is using the notch, so you must use the Q here, okay. Tangent based on the angle that given here, so you use this formula, okay, and until you get the Q. Okay, so this is direct question. Okay, so direct question you can get 5 marks or 4 marks to 5 marks, okay, for this question. Okay, so this is actually the previous final exam. Okay, so you just study that the example activity. Okay, now look at the trapezoidal. Okay, the trapezoidal, you must use this formula. Okay, so the trapezoidal like this figure. Okay, so you just put the value here, and then the trapezoidal weir with side slope 1, horizontal 4, vertical is known as Chipolati weir. Chipolati weir. So the discharge through a Chipolati weir is given as this formula. Okay, so this is Chipolati weir. Okay, with CD 0.63. Okay, but this is the other trapezoidal weir. Okay, with the trapezoidal weir with height side slope is 1/4, so you must use that is Chipolati weir. Okay, so in case they have the definition what is the Chipolati weir, so you can define that Chipolati weir is the trapezoidal weir with side slope 1 horizontal to 4 vertical. Okay, so now look at the example here. Okay, activity 5.5 example here. The Chipolati weir with width 0.5 cm is installed at a section of a channel. Calculate the discharge when the head over the crest is 0.25 cm. They give you the L, okay, the angle here, and H1 here, okay, and you get the angle here, tangent 1/4 here, so you get the angle here is, and then using the formula for the Chipolati weir, so just put all the value here until you get the Q. Okay, so this is the direct, okay, direct formula that you use and put all the value, and then you get the Q. Okay, so now we just look at the energy dissipator structure. Okay, so energy dissipator structure, okay, are commonly built at the lower end of a spillway, okay, to reduce the kinetic energy of flow. Okay, these structures are built to reduce damage caused by high kinetic energy flow. When designing an energy dissipator for a specific location, one must consider factors such as the site location, the dissipator structures, and the discharge through the dissipator. Okay, an example of energy dissipator is USBR Stirling Basin Type 3. Okay, Stirling Basin Type 3 is very stable with a steep jump, okay, front, and less wave action downstream. than Stirling Basin Type 2 or free hydraulic jump. It is recommended for discharge up to 18.58 meter squared per second per basin with fraud number 4.5 to 17, and velocity of flow V1 is 15.2 meter per second to 18.3 meter per second. So this is the designation. Okay, design the Stirling Basin type. Okay, so the type of Stirling Basin, okay, they have the type here, Stirling Basin type 1. Okay, they have the type 1 here. Okay, based on the type 1. Okay, so the Stirling Basin type 2, they have the 2 here. Okay, type 1 is no. Okay, Stirling Basin type 3, they have the 3 here. 1, 2, and 3. You must design. Okay, Stirling Basin type 4, so they just look like this one. Okay, so this is the hydraulic structure for Stirling Basin type 3 that you design. Okay, you must design in this chapter. Okay, Stirling Basin type 5. Okay, so they just only have this one. So, and the angle here. Okay, Stirling Basin type 6 is like this. Okay, so you must remember that the Stirling Basin types. Okay, so Stirling Basin type 7 based on this, and type 8 so based on this one. So now we in this chapter, so we just only design the Stirling Basin type 3 only. Okay, so for design in hydraulic structure. Okay, this is Stirling Basin type 6, sorry, type 9. Okay, and the type 10 here. Okay, so we know here. So this is the USBR Stirling Basin type 3. Okay, the type 3 you have 1, you have 2, and you have 3. Okay, 3 here for energy dissipator. Okay, untuk controlkan flow tu in spillway or in the dam, spillway dam. Okay, so this is USBR Stirling Basin type 3. Okay, to design. Okay, so USBR Stirling Basin type 3, there are 3 set of block. Okay, so they have the block A here. Okay, block B here, and block C. So like this one. Okay, so this is block A, block B, and the block C. They have the 3 types. So 1, 2, 3. Okay, so they have 3 types. Block A is called chute blocks. Okay, and block B is called the buffer piers, and the block C is end seal. Okay, so they have the L here, length from the block A to block C. Okay, and L2 is from the block A to the block B is the L2. Okay, to H3 is height of the block B. Okay, and T3 is the buff here. Okay, the width here, and S1 is the distance from the block A between 1 to 2 block A, and width 1 and height H1 here. S3 is the distance between the block B, and W3 is the width of the block B. Okay, so now you must to design this USBR Stirling Basin type 3, so you must know that the block A must have the H1 is equal to Y1, S1 is equal to Y1, and Y1, W1 is equal to Y1. Yeah, so this is the basic assumption that you must know, that block A and block B. Okay, so the block B, H3, okay, to get the H3 here, based on the H3, H1, Y1, and S1 is the same length. Okay, so the same length with the Y1. Okay, so that's why H1, S1, W1 is equal to Y1. Okay, H3 is this. Okay, S3 is this one. So actually this formula is given. Okay, actually this formula is given. Okay, W3 is 0.75, so T3 is 0.2. Actually S3 and W3 is the same value. Okay, and the T3 is 0.2 H3, and the Z3 is 1. Okay, so all the block A, block B, and block C formula is given. Okay, don't worry. Okay, H4 is using this formula, and the Z4 is 2. Okay, Z4 is actually the Z here. Okay, the value of the Z for the block C and C. Okay, so L2 is 0.8 times by Y2. L is referred to the chart of length of jump or on horizontal flow. Okay, so Y1 is equal to Q divided by B times by the V1. So you must know that this. How to find the Y1 first. Okay, to get the Y1 first, so you must know that Q divided by the B and times by the V1. Okay, because this using the rectangular, that's why they have the weekday. Okay, so they have the design for the stealing here. So the block 1, okay, block 2, sorry, block A, this is block A, block B, and block C. Okay, so this is the USBR stealing type 3, stealing basin type 3. Okay, and to get the V1, so you must know that the formula, the V1 here. Okay, the here our formula is given, and also the conjugate depth here. So the conjugate depth you have learned in chapter 3 and 4. Okay, you get this one. Okay, so don't worry, all this formula is given. Okay, so now length of jump on horizontal floor, so you can find from the this graph here. Okay, fraud number, you find the fraud number. Okay, and then you get the air over Y2, so you get the value here. Okay, and when you know the length, so you can find the Y2. Okay, so actually this table is to find the Y2 here. Okay, so step in sizing for USBR stealing basin type 3. So you must find the V1, Y1, fraud number 1, and Y2. Okay, step 1. Okay, step 2, determine length of basin L. Okay, determine H1, S1, W1, and the quantity of cube block or block A. So must use this formula. Okay, number of block A, B divided by S1 plus W1. So this formula is given. Okay, and also the number of block B is also the same here. Okay, B S3 plus W3 here. Okay, and then determine the H4 for NC block B. So that's the 5 step to design stealing basin type 3. Okay, so look at the example here. Okay, an 8-meter wide wheel of a dam is discharging 80 meter cubic per second of flow with H1 30 meter and HO is 5 meter. Okay, design and USBR stealing basin type 3 downstream of the spillway. Okay, so first step 1, find V1, Y1, front number 1, and Y2. Okay, so use this formula to get the V1. Okay, H1 is minus by H0. Okay, so H1 you know that 30 meter and H0 is 5 divided by 2. Okay, use this formula and you get the value of velocity 1. Okay, so you get the velocity 1, so you must find the Y1 based on this formula. Q divided by B times by V1, so you get the value of Y1. Okay, so using the fraud number 1 based on this formula, so you get the value of fraud number is 11.30. Okay, so you get the value here. Then you find the conjugate depth Y2. Okay, Y1 you get the Y1 to get the Y2. So just put all the value here until you get the Y2 is 6.668 meter. Okay, then step 2, determine length of basin. Okay, so from the figure of length of jump on horizontal floor, so use the length of basin based on this formula. Okay, so just put the value Y2, okay, times by 2.75, so you get the value here. Okay, now the step 3, you to find the H1, S1, Y1. Okay, actually this is and the block at the block A, so this is the same value. Okay, H1, S1, W1 is the same value. Okay, so to get the number of block A, so you B divide by S1 plus W1, so you get the value is 9.391. So this is the same as 9 block. Okay, so at the block A, they have the 9 block. Okay, now you step 4, determine L2, H3, S3, W3, and 3. Okay, based on the block B. Okay, so you find the L2, so you get this value. Okay, H3 based on the formula that in table given for block A, block B, and block C. So you just use that formula, so you get the 1.088 meter and S3. Okay, and S3 and W3 is the same value. Okay, and the T3 based on this formula, so you get 0.2176 meter and the Z3 is 1. Okay, so number of blocks, so you just use the B here, and then you get the 4.902 is the same as 5 blocks. Okay, so step 5, determine the H4 for N6. Okay, so you get the Z4 is 2 and you get the H4 is 0.7008. Okay, for the N6 block is only 1, so you just find the H4 and the Z4 now. Okay, so after you get this value, if question asks you to sketch, so you must sketch. Okay, so must sketch, then you must sketch like this one. Okay, so when the block A you get the 5, okay, you must have the block A 1 2 3 4 5. Okay, if in block B you have 3, also you must have 3 block. Okay, the answer just only 1. Okay, so you must refer to that you design that you get block A is 9 block. Okay, so if you get the 9 block, so in this block A you must put as the 9 block. Okay, and the block B you have 5 blocks, so they have the 5 block. Okay, so you must sketch that, draw the block A and B. Okay, and also the block C. Okay, so now this is the assignment. Okay, assignment for chapter 5. Okay, so I will give you the assignment that include the chapter 4. Okay, that's all. Thank you. Assalamualaikum warahmatullahi wabarakatuh.